Alright, so we'll start with Faraday's law of electrolysis. There are two laws. It's given in your book, so you can go through. But the first law states that the mass deposited or released during electrolysis is proportional to the amount of current passed or charge passed into the electrolyte. It means if W is the work done, it will be equal to the amount of charge passed, that is Q, or say it's directly proportional. So W is equal to ZQ, where Z is our proportionality constant or the electrochemical equivalent of the substance. And this is the unit of Z is coulomb per mass per column, sorry, mass over column. So that is our first law, and the second law states that when equal charges is passed through two or more electrolytic cells, and if they are connected in series, then the mass deposited at the electrodes will be in the ratio of their electrochemical equivalents. That is, W still equals to ZQ, or it's equal to EQ over 96,500. That is one column. So that is our second law. That means W1 over W2 will be simply equal to Z1 over Z2, and still equal to E1 over E2, since the amount of charge is the same. Q is equal to the same. Next, we move on to electrical conductance. So, under electrical conductance, or simply put, what is conductance? The ability of any substance to allow electricity to pass through it are called conductors, or the phenomenon is called conductance. And if it resists or it doesn't allow the current to pass through, then those substances comes under resistors, since they resist the flow of current. So we'll discuss something on conductors. Conductors, they are of two types. We have the metallic conductors and the electrolytic conductors. So what are metallic conductors? Any metals that allows electricity to pass through it are called metallic conductors. And there are some, and when we say electrolytic, that means it is in solution. Those solutions that allow electricity to pass through it. Suppose normal water is also it also behaves as an electrolytic conductor because it allows electricity to pass through it. But pure water, for example, pure water is not a conductor because there are no ions present in pure water. All the ions are removed, so there are no ions to carry forth the charges. Therefore, pure water does not conduct electricity. There are some differences between the metallic conductor and the electrolytic conductors. Here in metallic conductors, the charge carriers are the electrons, but in electrolytes, we have the ions. The ions are the charge carriers. Here, we don't see any chemical change. No chemical change. But in electrolytes, we can say that decomposition takes place. Decomposition takes place. Here, in metallic conductors, we don't see transfer of mass, no mass change. no mass change. We don't see any change or transfer of mass. But in electrolytic, we can encounter transfer of mass. Transfer of mass because uh, in suppose in a galvanic cell, you will see we can see that deposition of the ions takes place in the electrolyte, in the electrodes. Therefore, we can say that transfer of mass takes place. Here, if we rise the temperature, then the resistivity goes up. That means the flow of current is not uniform once you increase the temperature. That means the conductance goes down. But here, if we increase the temperature, it's the opposite. The resistivity goes down. Because once you raise the temperature in a solution containing electrolytes, then there will be more movement of the ions. Therefore, there will be more conductivity. And so these are some of the differences between the metallic and the electrolytic conductor. You can also go through those things. Next, we'll go to molar conductance. It's denoted by capital lambda M. And what is molar conductivity or molar conductance? Conductance of a solution containing 1 mole of an electrolyte between 2 electrodes, which are unit length apart. It's called molar conductivity. And it's related to the Lm is given by kappa volume, kappa in volume. So we can say that kappa in 1000 over concentration, or simply put, molarity. That is our molar conductance. Now, so for equivalent conductance, you just simply change this to normality. Equivalent conductance. So that will give us our equivalent conductance. So here's an example. They've given us the resistivity of 0.8 molar for the simplorate solution, and we also calculate the conductivity, molar conductivity. So we know that the molar conductivity is equal to kappa into 1000 over molarity. So if you plug in these values, then you'll get the answer. But before it, they've given us the resistivity rho 2.5 into 10 raised to the power 3. So that is our kappa. So our kappa would be nothing but 10 raised to the power 3 over 2.5, which is 4 into 10 raised to the power 2. So if we plug in these values, we'll get the molar conductivity. ohm centimeter square per mole. So let us try to understand the behavior of conductance according to concentration, and in terms of the strength of the electrolytes, if it's strong or weak electrolyte, there will be differences in the conductivity. Now, conductivity always decreases. Conductivity always decreases with the decrease in concentration for both weak and strong electrolytes. For both strong and weak electrolytes, conductivity decreases. Conductivity decreases with the decrease in concentration. With decrease in concentration, that means suppose there is a 1 molar solution of either of the two electrolytes, a strong or weak electrolyte. Once you go on diluting it, so once you dilute it too much, then the conductivity will decrease. The transfer of ions will significantly be poor. The second point is that the number of ions per unit volume that carry the current in the solution decreases on dilution. That is the reason why on dilution, conductivity decreases again. Since on dilution, conductivity decreases. Because there will be less number of ions per unit volume of the solution. The other point, molar conductivity increase with decrease in concentration. The molar conductivity, that is our lambda m, it increases with decrease in concentration. It's because the total volume of solution containing 1 mole of electrolyte also increases. That is the reason why the molar conductivity increases with decreasing concentration. Next point, molar conductivity is the conductance of solution. Molar conductivity is the conductance of solution. And then when concentration approaches zero, that means at infinite dilution, the molar conductivity is known as limiting molar conductivity, and it is represented by the symbol lambda naught. So at infinite dilution, that means once you keep on diluting the solution, it is called the conductivity, the molar conductivity is called as the limiting molar conductivity. So these are some of the behavior of or variation of conductivity with concentration. Collard's law. This will be our last topic for this particular chapter. So what does Collard's says? At infinite dilution, when dissociation is complete, each ion makes a definite contribution towards equivalent conductance of the electrolyte, irrespective of the nature of the ion with which it is associated, and the value of equivalent conductance at infinite dilution for any electrolyte is the sum of contribution of its constituent ions. That means at infinite dilution, the molar conductivity is nothing but the sum of the individual ions, the anions and the cations. for example, the conductivity, the equivalent conductivity of say sodium chloride will be equal to the conductance of sodium ions plus chlorine ions. So that will give us the whatever values individually they contribute will be the contribution of the total complex or the electrolyte as a whole. So let's try to do some examples. Calculate the molar conductivity of oxalic acid given that equivalent conductance of sodium oxalate 400 around centimeter squared. Sulfuric acid 700 per mole. So that is our question. So we have to get the conductivity of oxalic acid. This is our oxalic acid. So if we combine these three, we're getting this one. So our equation for this would be something like sulfuric acid give us our so this is our equation. So if we add this two and subtract this one, we'll get our acetic acid. But the thing is here, for sodium sulfate and sodium oxalate is given in equivalence, but here sulfuric acid is given molarity. So we'll convert all the molarity in. So if we convert it, our equation is something will look. So we'll give us 600 centimeters squared per mole. Now the equivalent conductance be 400 plus 700 over 2 minus 450. So that will give our equivalent conductance 350. So 350, 750, 7 just 50 give us 300, and then our also 350 minus 50, 300. So our total molar conductivity is 600. So there are some applications of Collard's law. So application is given in your book also. But so from One of the application of Color's law is our degree of dissociation, or simply put, dissociation constant, calculation of dissociation constant. Dissociation constant. That means the equivalent conductance will be always lower than the degree of dissociation. So if our degree of dissociation is alpha, then it's given by the ratio between these two, that is equivalent conductance equivalent conductance at a given concentration, equivalent conductance at a given concentration over equivalent conductance at infinite dilution. So that is our molar or our dissociation constant. So that's it with this chapter. I suggest if you have any queries, you can ask me through my. You can text me my number. We'll start the next chapter in the next video.